Greetings. This is our ENE350 lecture for October 28, 2013. And we're going to continue to talk about bootstrapping in kernels. We began our discussion last Wednesday, and today I will try to connect the block diagram description that we talked about on Wednesday with the actual code that I will share with you in just a little bit. So to get a little summary of what we did, in this diagram we have basically color-coded different parts of our kernel process. On the left-hand side, you see the bootstrapping space, where we have a two-level bootstrapping process, a base bootstrapping code whose job it is to copy the extended bootstrap code into this so-called green space, which is our physical space of memory for our Vesp. And then there is actually what's called a disk space. So really there are three different spaces that we're talking about here. One is the bootstrap space, and one is the physical space of Vesp, and then the kernel space. The disk space, which does include a copy of the kernel. So in order to be able to differentiate between these different parts of our extended space, we use what we call a virtual address register, which happens to be only 4 bits in this simple implementation of Vesp. And when we set this particular register to 0, which is to say 40 bits, that refers to our green space, which is our physical space. So the remaining 12 bits will give us 4096 locations in this green space. So, and these locations will be further refined into different portions, like the register space, extended bootstrap code, keyboard variables and drivers, screen variables and drivers, and kernel and OS, and then the application heap. The disk memory itself will have some more capability, will give us the capability to store more programs in our architecture. And of course the yellow area is where we maintain our bootstrap code and the extended bootstrap code. Those are the different places of our memory. Now if I go back to if I go on to the Xcode representation of this particular implementation of Vesp, which is our kernel implementation, you can see how all of this is tied up to an actual code, which makes it work as an actual kernel process. And we saw an example or two of this in our Wednesday class when I managed to, read a program in from the terminal and then execute it and then display also the program that we had actually entered through the kernel layer of this machine, Vesp. So one thing that I want to mention at the very beginning is that the code that we develop here is built on a more extended instruction repertoire. This version of Vesp, which is Vesp 30K, includes 37 instructions as opposed to 16 instructions of, let's say, Vesp 2.0 or 2.1 or all the other versions prior to this. And what these new instructions do, they provide additional capabilities and flexibilities. For example, the add instruction now, that this is the original add instruction, which actually adds 2 operands, one in A and one in B, and then puts the result into A. Now that we have a dual add instruction where the target of the addition operation is B, and for that we have a different code. So you can see that how we the way we extended the instruction opcode for this was by way of adding a second hexadecimal digit. So this add instruction now is 00, whereas this new add instruction is now 01. So you have to write these in order to be able to affect these instructions when you actually develop your code. Some are still maintained as, like single hexadecimal digit numbers, opcodes, because we haven't really expanded those. Only those that we expanded now require 2 hexadecimal digit specification. There are other instructions that have been added, and we have subtraction instructions here. For example, we could actually subtract B from A or A from B and then put the results into A or B. And then we have more enhanced jump instructions. We can jump on 0, we can jump on positive, negative, greater than or equal to 0, less than or equal to 0, not equal to 0. Those are all capabilities we added. We have shift operations that actually are now applied to the B register, not just the the A register in the old version. And then even the AND and then the OR instructions now can actually be affected onto the B register side of the computation. And then we have, of course, again, we've added increment and decrement operations instructions for register B and register IX. So those are the things that we added. Now, this code is in the preamble. I've also added a sort of like a memory map here, just to make the block diagram representation a little more precise. So when you look at the memory map here, you see that we still have A and B registers in those two locations. We got the IX in the third location. Now the VAR takes up the space which we call location 3 in this physical space of VESP. And then we have the stack pointer, the interrupt register, 2 more registers in here which we call GNH. And then we have the bootstrap code that begins somewhere down here, which includes cursor information. When we think about the screen, the cursor will be at a position on a plane, and so we need an X and a Y coordinate. Not all of these pieces of information may actually be used or demonstrated in this version of VESP, but I've added these things in so that in case we want to, let's say, emulate some coordinate behavior on the screen of our VESP, these registers can be exploited for that effect or to that effect. We have a location in which we store space, a location in which we store carriage return, and all those things. Some locations are reserved, as we call it as such, and these would be actually locations from, for example, 10 to 1F. Now this is the physical space, so I'm still using 3 hexadecimal digits, as you notice here. And the boot vector takes up the space from 0 to 0 to 0FF. This is where the boot vector resides. And this boot vector is actually this this extended code that we talked about here. This extended bootstrap code is what I call the boot vector. That boot vector is copied into this location by bootstrap code. So going back here, the boot vector ends in here, and then after that we begin our keyboard driver and ASCII tables, and then the frame buffer kicks in. Now the frame buffer takes up some 4 blocks of memory. As you can see that it begins at 300, it ends at 6FF, and so there are 4 such blocks of 256 locations. The reason that we have that many blocks, if you think about it, 4 blocks make up 1024 locations, and that's precisely what a 16 by 64 screen will actually take up. That is to say, 2 to the 4 times 2 to the 6 gives you 2 to the 10, and that's the number of locations we have in this sort of setup. And so that's our screen, by the way, meaning that we have 16 lines of 64 pixels. Each of those pixels can, of course, have 16 bits of information. If we think of this memory as holding 16-bit worth of information in each of its locations. Where do we get to use all those 16 bits? is not really critical at this point, because all we want to do is to lay out the template of the screen, and then whatever we enter into those locations is something that will decide ultimately how that screen gets manipulated, what depth that we actually allocate to the pixels in terms of their color and other properties. So that is not emphasized in this discussion. Now, that was our screen right to this point here, from like 300 to 6FF. And again, I've been using 3 bits of information, 3 hexadecimal digits of information for these locations, but then I've added 0 in there just to emphasize, I guess. In fact, that kind of began right up here. I just added that 0 because this location now has become 1. I could have still avoided using these zeros, but now I'm actually using the full 4 hexadecimal digit span of our memory, which goes up to 64K, not just 4096. But these bits are still set, these hexadecimal digits are still set to 0. Now down here, right after the screen or the frame buffer up here, we actually put in our kernel code. This is where the kernel will reside, and this is where it's going to be executed from. So whatever kernel code that we develop will be copied over here in order to make this kernel emulation a reality. So those are 3 pages of or 3 blocks of 256 locations where we will have our kernel code. And then after that, we got some user space. So the user space that we have has, it begins at location A, and each of these locations will actually have 256 words. Those 256 words will have will be enough for each of these users. I've just given this space to some 6 users, and that doesn't mean that they have to be different 6 users. They could actually be all the same, but these are locations inside of which we're going to store some user programs. Like we may write some program and then copy it over here, and then we can write another program, copy it over here, and then this can continue all the way up to these the last place where we have the last user's program will reside. So once this is over, once the user space is also allocated, you notice that we've actually come up to a point where this is called like 0F. So if in fact we go to the end of this, so we're going to go to 0FFF here, that means the next place that we're going to have to start out will now be 1000, which is actually up here. So now that we have switched from the physical space to the hard disk space, we can just lay out the structure in the hard disk. And that, of course, part of this hard disk will also include a copy of our kernel code. That is to say, the original code will always be in the hard disk, and that will be copied straight into the physical memory at the top here. That's what we call the kernel code operational sort of like copy, because we can only execute out of the physical space, not so much the hard disk space. We're going to have to copy that particular code right down to here. So from the hard disk, where the kernel code will reside, a permanent version of it, well, then we have to copy that over into the actual physical space where VESP executes its programs. So now that we have that, that's actually like laid out in there. The last portion of this memory map is the bootstrap code, and I think in this sort of version of it, when I think about this now, it looks as if that I'm actually giving the bootstrap code a little less space than I initially thought. So that means I'm actually increasing the hard disk to include some more chunks of memory that begin with hexadecimal digit F, for example. I'm actually using all the way up to EFF. That means the next time I start out, I'm going to have to start out with FF00, and that means my bootstrap code will actually be limited to 256 locations. So that will just bring me to the end of my virtual space. Virtual space meaning that, you know, the physical space plus the hard disk space plus the bootstrap code. When all these three spaces come together, they make up the entire space of my machine, so-called, you know, VESP's virtual memory. With this virtual mapping, I can now basically store some of my programs in the hard disk, some of them in the physical space, and of course the bootstrap code is just there to make sure that when I initiate my computer or when I just like, you know, do a cold start on it, then it's going to just like kick in and do its work, and then after that the control is turned over to VESP itself. Now the code that I've written to actually do the kernel version of VESP is going to differ from the earlier versions. In the microprogram version, for example, we added a different layer underneath the machine layer, and that layer allowed us to, as we talked extensively about this when I was in the US, what that allowed us to do was to emulate the machine level operations by what we call the micro level operations. Now at this point, in this particular sort of situation, we're going to have kernel computations. So that means we're going to have to really let the control go into the kernel layer and then relinquish, you know, essentially control from the machine layers to the kernel layer. So what that means is that all we have to do is, in the main code, is to initialize. That's what we're doing here. And then once we get the initialization completed, just kick the machine into bootstrap. So you can see that we're not even calling the main program here anymore, as we had in all the prior versions of VESP. We really allow our machine now immediately go to what's called the bootstrap, and this bootstrap has to include in it this copying process, which I mentioned earlier, which if I can go back to again this PowerPoint presentation version, in here we have this bootstrap code. That bootstrap code will have to come in now, and that's what this particular code is referring to, this bootstrap code right there. So let's go down and then take a quick look at that for just a second, so you get to see what really happens. Now, if you recall, at the top here, just take a quick look. We said that our extended code, the bootstrap code, will actually reside. We'll start taking locations from 20, 0, that is 20, you know, down to FF. So the thing that we're going to do is we're going to copy the so-called the extended kernel code into location 20, begin there and then continue from there to FF. And so when I go down here and simply make that copying, which is in this bootstrap process, what I'm copying is some preliminary code that is in the bootstrap memory, which needs to be copied into the physical memory of VESP. And so I identified really two types of memory in here. One would be that thing which we call the VESP's main memory, and the second one of which is the bootstrap memory. So when I go to this bootstrap place, you will see that that bootstrap memory actually is there. Let's just actually go and take a look at that. Let me just go down a little bit. Okay, there it is, right there. So if you look at this bootstrap code, which we would call as the first function, you know, as the first functionality, as soon as our machine begins, right after the initialization process, which clears certain registers and, you know, defines other things, which is in some ways similar to the initialization processes of the past versions. We go to this bootstrap piece here, the shaded code. So what this bootstrap does, as you can just like look at this for loop, for example, what does it do? It simply says copy some number of locations from what's called the bootstrap memory right there. to what is called the memory address. So that memory address is basically where VESP has its physical space. Now you see that we are doing a little translation. What is in location 0 in the bootstrap space goes into location 20. What is in location 1 in bootstrap space goes into location 21. This is in hexadecimal, because the purpose of that is that we really begin at location 20 for our bootstrap code, and the reference that we make here is actually this reference here. Let's see if I can just bring that up. If you can focus on that highlighted code, what that does in the PowerPoint version right there. See if I can actually bring both of these in there just a little bit right there. So what you see here, the shaded code here, is actually some location in this section right there. In fact, if I call this the bottommost address right there, I'm trying to highlight that in some ways, but it's a little difficult. Like within this yellow space here, the bottommost in this, and right over the, like the separation line here, is that first location. So it kind of goes from here to the bottom of this rectangle here to the top of it. You get all the information, all of the extended bootstrap code. So what I'm doing is I'm copying that by way of this bootstrap code and through this for loop right there into what's called the VESP memory address plus 20. That is to say, I'm actually going to not to the topmost location, but to somewhere there, which is actually location 20. That's why this translation happens right there. Now, once I finish this, once I actually finish this copying, the thing that I do is to initialize the program counter to hexadecimal number 20, because that's where my extended code is going to be, and then boot the system. So all the bootstrap program does, is to copy this yellow portion into the green area, that is our VESP's main memory, and then after that just call up the boot function. And what the boot function does, it actually executes whatever is copied into that green section. We can even take a look at that right here. Right there, that's our boot function. Now, we just have to understand what this does. So what the boot function does, it actually serves a number of purposes, and these are all commented in here. One of the things it does, for example, it clears the frame buffer. I'll explain the number of iterations in each of these for loops, so that that'll be evident to you, that clear to you, that in fact these loop iteration counts are very carefully computed, and to get the VESP machine to accomplish these computational goals of the kernel version of VESP. Now, in each of these functions, if you notice, in each of these loops, not functions, but inside this boot procedure function, we actually invoke the main cycle, and we invoke it only once in each iteration. This 0, I guess, is just an index or an argument that determines how this main cycle will actually display its operations. If I put a 0 in there, it'll be invisible. Whatever it does, we won't be able to see any effect of that in terms of the display that we get to see. The only effect of that would actually be the execution of the instruction that particular iteration corresponds to. And then, so the first thing that we do is to clear the frame buffer. Now, this 4,254 that you see here, that means like that many iterations that we have to perform, comes from the fact that as we try to clear the screen, we actually have a loop, which is a VESP instruction program, which takes about that many instructions to execute to clear the frame buffer. If you just hold on for a second, I would say I'll go back there and to the place where the extended bootstrap code contains this portion of the kernel processing, and you will see that this count actually comes about extremely delicately as we count the number of instructions that get executed in that portion of the extended bootstrap code. So the boot basically mechanizes these different portions of the extended bootstrap code. And in the next group, for example, all we have to do is just write Vesp is booting, or just Vesp booting, and triple periods in there, and you can see that now we go from 4,255 to 4,272. Effectively, if you just count how many iterations in there, so 72 minus 55, and that's 12 plus 5, that's actually 17 plus 1, 18. So it must be that I think we have probably that many steps. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, I guess is what I've counted. So let's see, did I count this the right number of steps? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 steps, and here we have 15 plus 12, 17. I guess I have to tie these together somehow. I count here to be 14 characters displayed, but this happens to be 17. So we have to maybe connect that with the actual number of characters that get displayed. We'll just take a look at this. If there's any discrepancy between the number of cycles that I need to execute and the number of iterations that I'm doing here, we'll find this out when we go back to the code. Maybe there are some other things that I'm actually doing there, and this doesn't quite accomplish this. This little comment may not be all of it. Now, here's Vesp is booting portion, and this is the actual display, and for that we just have to update the screen. That's line 0, and that's actually 64 characters wide. And then we get a bit of a delay, and then we write loading kernel, again, 4 dots in there. Now let's see. In this situation, again, we seem to have counted from 4,290 down to 4,273. That gives us 18 iterations, and so that should somehow correspond to 1, 2, 3, 4, 5, 6, 7, 8, 9 maybe, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I guess maybe I just counted more than one space there. So this roughly matches, and we have to be a little more precise about this when I get back. So what this is basically doing is, you can see now, we're writing these things into the actual memory of Vesp. That will be the screen area for sure. And then after that, we update the screen. That's loading the kernel message that we've just written up, and we're now displaying that in the next sort of like a set of steps. Now, the reason that I actually have two lines 1 and 2 in here, because I leave a bit of space, just a line of space as a carriage return, and then just display the next group, which will be this loading kernel comment or message. After that, I go in and do another quite a few number of iterations in here, and that actually is for the loading of the kernel from the disk memory into the physical memory. And then the only thing that I have to do after this, once the kernel is copied over into the physical memory, I just do one iteration, in which case I'm just copying, or I'm jumping rather, from wherever this code would end up at to the very first place where the kernel operations will begin. So once that happens, now I have to really call the kernel. that is the kernel function, has to kick in. So this is where things really get a little bit involved, because now we have the machine code that's going to emulate the kernel, but that in and of itself is an emulation, and so we now have to invoke this kernel process. So whereas down here we just simply made one iteration of this main cycle to jump to the place where the kernel code begins. Now from this point onward, the kernel program itself will actually force VESP to run from that point onward. In other words, wherever the program counter is initialized to at this point is where this kernel code will pick up the steps, and then now we'll execute a whole bunch of things like load, and then store, execute, read, write, all those things that we actually wanted to ordain this particular version of VESP in order to carry out the computations at this level. So I'm going to actually end my lecture today. I guess I'm going to stop when I get to the point where I'm going to have to explain these individual execution pieces here for the 4 or 5 commands that we define, and I'll handle that for the Wednesday class. So let's get back here. Now that we've reached to get down to the kernel step, let's see exactly how this copying, not copying so much, but how the extended bootstrap code is executed, because we did manage to execute lots of iterations here of code, as you can see, before we even got to the kernel. And these iterations are pushing the extended kernel code, or pushing through that code and trying to accomplish a bunch of things. And those things, of course, include, as we already talked about, the copying or clearing of for example, the screen, and then messaging the user that in fact certain things are happening, like VESP is booting, loading the kernel, and so on. And then, of course, we got to get this update screen function called in so that these text messages actually get displayed. This is what really this is. This update screen is just like a little piece of hardware it's supposed to be, where the video buffer gets dumped onto the screen every single time some changes happen in the frame, in the video, or the frame buffer, so that the screen is kept up to speed with the changes in the actual buffer. Now, so the 4,000 some steps in here is for clearing the buffer space. The computation of this is not that hard actually to do. Let's just go back to the place where now these instructions in the extended code are stored up here. And this is, of course, in the initialization step. This bootstrap memory that includes or contains, again, looking back in here, in the extended space, we dumped into here some code, and that actually is initialized here. Now keep in mind that this initialize step is the first thing that gets executed before we even get down to this bootstrap here. So if you look at here, you see that initialize precedes the bootstrap. So in the initialization process, we get to put into this bootstraps portion the stuff that would be copied from the bootstrap memory into the physical memory. So that means this extended bootstrap code, which you now see in here, will have been copied to the VESP's main memory. That, of course, took place down here in the bootstrap code, as we saw. Okay, that's where the memory portion of VESP's architecture picked it up from the bootstrap portion. Because we implement or we execute this bootstrap right after initialization, whatever actually was dumped into the bootstrap in the initialization step, which is that up here, is now going to be in the Vesp's main memory. So this initialization is just putting things into the bootstrap, but then the bootstrap function copies everything that we put into these locations into the main memory of Vesp, beginning at location 20. So the actual code that you see here, the machine code, is what takes care of the clearing of the screen. That's the first portion of what we get to do. So here, for example, what you notice is that we, just for emulation purposes, clear location 8. That's what this is. Cursor X it was. Cursor Y it also gets cleared. And then we set the location A to pixel color, because that's how we define it up here. We called it the pixel color. Not that we actually use it, but just so that we give it a meaning. And if it were to be actual color, right there, location A, that color will be will actually be functional, and whatever we display will be in that color. We're not using that, but we're just writing it down here so that that effectively is emulated, just pretended to really to do that for a function that is not implemented in this kernel edition of Vesp. And then the display mode is ASCII, so we set that. And then the pixel symbol is set to plus sign. These are things that we get to do in the bootstrap code itself. And so if you look at all those things in here, once we get this done, now we're going to clear the screen. So let's just think about this for a second. What we're really doing here is we're doing some load instruction here. As you can see, that's a load instruction. And that load instruction is setting the IX register to 300. That means that's where we're going to begin clearing the screen. Because if you remember, our screen began at location 300 up here, frame buffer. So we're going to clear these locations, meaning that we're going to put blank in there, spaces. And so the IX is initialized here to 300 in this fashion. So we actually, location 2 is our IX, so into this IX we put the number 300. And then we put in 400 into register A. This is actually the count of the number of locations that we will have in our frame buffer. Keep in mind that our frame buffer was a 16 by 64, was supposed to hold an image of 16 by 64 screen, and that gives us 1024 locations. So what we do, we copy that. That happens to be basically, in a way, a count that we have to keep track of as we increment this 300 and then try to reach all the way to the end of that a buffer space. We're going to have to deal with this particular value of the counter. So we set it to the maximum value, and we're going to basically keep decrementing that until we get to a point where we no longer have to clear any place. So then we load space into location D, and then we simply say if A0, and by the way, as I just said, we put that 400 into A, then jump out of the loop. So to basically get done with this whole process. If not, if that A is not equal to 0, you decrement it, decrement A. That's what this instruction does. And then you loop back to check if A is equal to 0, which is what this instruction does. This is a force jump back into location 20. And that is the location where we simply check to see whether this thing is actually equal to 0. Okay. Now, if not, we just go ahead and insert a carriage return at the end of each line. So what that means is that we're going to have to now that means we're done with this process of actually putting all the spaces. That's what this portion of it was all about. Now that we've finished with that, we also want to put a carriage return at the end of each line. So that means that we're going to have to do a count of 16 this time, because there are 16 lines, as opposed to like count of 1024. So the way we just actually created the screen, or clear the screen, was first of all make everything space, and then so that we can mark the end of each line, we now are going to have another loop here, a smaller loop, much smaller, to keep inserting a carriage return per each line. And then there is a loop that actually ends up here somewhere, right there. So if a is equal to 0, then jump out of the loop. If not, then keep going back. Okay. So this whole thing here is actually all about that. Okay. We keep going back to the loop after we change we actually insert the next carriage return. Now once we get that done, we write into this bootstrap space, which gets copied into the physical space of Vesp, that is vesp.memory. Now the message Vesp is booting. So all we do is we write these things. Vesp space is booting. So however number of instructions we have here is the number of iterations of that so-called boot function is supposed to have. Now in this situation you can see that there's one instruction, a second, and a third, and a fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, and 18th, right there, all the way to the 18 instructions in here. And so that actually happens to be 18, so I guess I must have counted it wrong in the earlier going. So 18 instructions will take care of this copying. And then after that, we write display load in kernel. Again, all we do is we have a bunch of load instructions in here. These load instructions take care of just this message. And you notice that all of these letters are actually written into certain locations inside the Vesp's main memory. Like this L goes into location 340. O goes into location 341. Now these are the locations where our screen will display these messages. And keep in mind that we begin at location 300. So the fact that this is actually 340 tells you something about where this particular line begins. This is actually line number, if you just think about this, like over here, let's just go and take a look at this. And we were writing this first line here. It said Vesp is booting, so we put that into location 0, 0, and then to 0, 1. So that was the first line. Now they will run up for up to 64 places, and then we'll just, having completed that first line where we say Vesp is booting, and that happens to, by the way, not just 0, 0, but 300. We go up to whatever number of characters we have, which happens to be 311, and then we kind of stop there, and then now the next one has to start at the next place. So if it's only 64 characters that we pack into each line, that means that 3 now must actually, not 3, but that next group must begin at 40. That is like 64 here. Okay. So having packed the first 11 characters, or 12, whatever number, it's actually hexadecimal, it's more than that. We just counted that to be about 19 here, as you remember. Now we go to the next line, that is 40. That is loading kernel portion goes into that next place. And then it gets written in. That's the sort of like message that says now the kernel is loading. And then that means now we can actually start loading the kernel. And loading the kernel takes a certain number of clock cycles because we're going to copy now, as it says over here, a whole bunch of things from, for example, these actually were 300, I'm sorry, this was 3 blocks of 256 words. Some 768 locations will have to be copied, and however many instructions we have to execute in each of these iterations, in each copying process, because we go out and get a word out of there and then put it back in. From the hard disk we go into the physical disk. So, but to do that, we actually do quite a few instructions in here, as you can see. Okay, there is a loop in here. So here's the loop portion of this, for example. If A is 0, then jump out of the loop. If not, just go ahead and do this. So effectively, what we need to do is to count how many instructions we actually execute. So here's one instruction, for example. Here's another instruction. Here's another instruction. Here's another instruction. So 1, 2, 3, 4, 5, 6, 7 instructions, and then an 8th instruction here. So we got 8 instructions inside the loop, and so we're doing about 768 copying steps. So in each of those copying steps, we get one of those kernel instructions that resides in the hard disk and copied into the memory. So that effectively we need to multiply 8 by 768, and whatever number that is, and you can kind of see that that's going to be roughly 5,600, a little more than that actually. What is that? 8 times 768, so that is 5,600, and then another 400 or so. So about 6,000 cycles must be actually consumed for all these instructions for this copying process to be completed. And indeed, if you go down here, let's see how many iterations we actually performed in there. Take a quick look. This is the step where we do the kernel loading right there. So 11,206 minus 4,291, and that's actually a little less than 7,000. So I think our computation is a little off, but not much. That's because we possibly multiplied something by 8, whereas we should have multiplied it by 9. We can go back and count how many instructions we would have actually gotten. We would have executed. Let's see one more time. Up here, we need to go back up a little bit. Yeah, right there. So we are at the top of our loop here. 1, 2, 3, 4, 5, 6, 7, 8 it seems. So it's actually 8 instructions. So 8 times 768. Let's see what number is that? So it is like, okay, 56, 48, 53, and 56. That is plus 56 plus 5, 61. I compute it to be 6136. Let's just make sure that we get this right. And if it's 8 or 9 instructions, we got to be careful. 768 times 8 is equal to, yep, 6144. So that is probably not enough to make this differential that I just looked at over here. Let's see if in fact I can count this accurately. So here's my loop. That's outside of my loop. There's one instruction there. Oh, there are 2 instructions in here. That's what I was not counting. So 2 instructions right there. 1 there. That's 1 instruction. And this is another instruction right there. That's 1, 2, 3. That's 1 instruction. 4, 5, 6, 7, 8, 9. So if I, instead of that, if I multiply it by 9, Let's see if I can find my calculator here somewhere. Where did it go? Uh-oh. Let's find it out here. Find out where that disappeared. There it is. So clear 768 times 9 is equal to 6,912. That's exactly, I think, what this number of cycles. Of course, we have to add, by the way, the preamble here must be added. A few more instructions, but now let's go down there and then subtract now. Let's just go ahead and do that as well. So I'm going to subtract now, clear this. So I'm going to take this number 11, 12, 11, 206 minus 42, 91. That's roughly, okay, 6,915. We had found that to be 6,912, but we have to add to the count we had the portion, which is here. There are 3 instructions which we have to add. That's exactly 6,915. That's the number of cycles we have to execute to do this copying process. And of course, I didn't really count how many iterations we would need for the clearing of the screen, for inserting space characters in there. For that, you really have to count this loop here, this loop there, like here. There's a loop. Not that one, but somewhere in here it has to be the loop load space if a is 0. So there's your loop right there. Loop back right there. So those are the instructions. So you have to multiply. Here's a load instruction. Here's a jump. Here's actually another instruction, which is a conditional, not a conditional, which is actually a MF, I guess this is MXF instruction. And so that's one load, and then second, and then third, and then fourth instruction, fifth. So it must be like 5 times the number of times we actually go over this iteration. That's 1,024 times 5. That's roughly 5,000, well, that's actually 5,120 iterations, plus a few more at the beginning and at the end, if there's any. And that means that loop, which actually inserts the space in this bootstrap process here, must be about 5,000 number of steps in the boot process, not so much bootstrap right here, down here. Okay, so this is the clear frame buffer process. Yeah, so 4,120 or something is what I said. But that next portion of it, which we did not actually take into account, was this loop, the second loop that we just didn't count. And that was a smaller loop, much smaller loop. And that is this initialization of the index register to 10. So we're doing only 16 lines, but for that we execute a bunch of instructions right here inside the loop. So we have to multiply the number of instructions in here by about 16, by 16 exactly, and that will give us how many iterations of this. So that's how you really computed these numbers of iterations here in this particular sort of like boot function right there. So that count, which we already explained, and this count, which we also, not that one, but this one at the top, this one right there. These numbers, that's 4,254 iterations of this main cycle. That actually clears the screen, as this says, and all these things do whatever they're supposed to message in terms of like what gets written on the screen. Those are those steps. And so that really takes care of the initial steps. Now once we do this, as you notice up here, we're done with copying of the bootstrap memory into the Vesp memory. If we complete doing this in here, And by the way, you don't see the copying in here because these are machine instructions that really get copied. This is what we're copying. These are the instructions we're copying into the VESP main memory. This copying itself, as I've been saying, even like last week I mentioned this. This copying takes place is done by this bootstrap code. So you don't really see. If you look at the code here, you don't see any VESP memory up here. Up here, there's no VESP memory. Everything's bootstrap because what we're doing here, we're simply copying, writing these initializing. I'm sorry. Hold on, I think I got something opened up here. Close that. Quit that. So this is the initialization process. We're just simply writing these instructions, codes down into these locations in the bootstrap. The copying process from the bootstrap memory, which this is, to the physical memory, the VESP dot memory, happens to take place right down here, right there, in this for loop. Okay, that's where the copying takes place. And of course, there's only 84 hexadecimal locations is what we copy because that's the extent of the number of locations that we actually occupy. If you look at it here, we begin at this location, at location 0, and we run up to, just keep going down here. It's the bootstrap, 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 bootstrap. It ends somewhere down here at location 84 or so. Right there. It ends. This is what we're copying into the main memory. And as you notice, the last instruction that is actually copied or stored in the bootstrap code, extended bootstrap code, is 4700, which is like jump to location 0700. That location, by the way, is where the kernel begins. Right there. Kernel begins right there. So, to wrap things up, all we do in this portion is to have, if I could just go back here, is to copy this code into the space here, and then relinquish or pass the control to the VESP, where VESP would simply now wait for the commands to come in from the user end, so that these kernel commands can be executed. I didn't quite get to explain how the kernel commands are actually coded, but what we learned in this particular lecture was that we did the copying of bootstrap memory into the VESP memory, but in the copying process we also had to populate the locations in the bootstrap portion of our kernel layout, memory layout, and which we did over here. And of course, together with this, we're also emulating this process. We had to go out and execute the copying process, that is copying of the code from the bootstrap memory into the kernel memory, and that gets done in the bootstrap code as I explained just moments ago. But the initialization process itself is actually taking care of these so-called processes of initialization, as well as clearing of the screen memory, the buffer, video buffer, and then ultimately copying of the kernel code. Now, of course, it's the boot function, not the bootstrap, that will execute these steps, and you saw that happening as well down here in the bootstrap, in the boot code right here. These for loops here, there's one there. That's the one that clears this frame buffer, and this one is just writing boot. VESP is booting. I guess what was missing was there is booting. So if I now count the number of characters, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and that's exactly what this is. 18 18 iterations. That is 72 minus 55 plus 1 is exactly 18. Okay, so that gets clarified. And so these for loops are there to execute what we initialized our bootstrap memory to, but we didn't execute it in the bootstrap memory. We actually executed it in the Vesp main memory, and that copying took place in what's called bootstrap memory, a bootstrap function right there. So all the bootstrap did was complete the copying and then pass the control to location 20, which then allowed us to execute out of the location 20. But that thing that we executed was Vesp code, and that code was copied one more time through this for loop into the memory of Vesp, which you see here is happening. That copying, of course, had to be done before we give the control to Vesp to execute that code, which was, again, if I could just say it, was to clear the screen, which we're doing here, clear the frame buffer, put this message out, and then copy the kernel from the hard disk to the main memory. We can't compute all these, not that one, but the one below that, here, and then be done with this part of the process. Once we get this done, we go and jump to kernel. So jumping to kernel will initiate the actual kernel process, which is to say, whatever commands that we're going to build into the rest of our code, which is contained in the kernel portion of our bootstrap code, which we copied from the hard disk, will now do all of the kernel instructions. So I'm going to cover that in the next class, in my next lecture, which will be done for Wednesday. But I want to end this now because I think I might have actually spoken for maybe more than even 75 minutes. So that should be about lecture worth of time. But if you have any questions, please shoot them in my direction. I'll be kind of like stationed in this location through the end of next week, and then I'll get started to head back to the United States. So until I guess our Wednesday recording, everybody take care, and like I said, email me your questions, and I'll be happy to answer them. In fact, I expect that some of you will send me, will email me with questions because I plan to assign you homework where I would ask you to add some more commands, kernel commands to this code. Now, as I said in my our Wednesday class lecture, this thing will not be, the kernel material will not be included in the final. So whatever you prepare for, it has to be for everything that we've done through the end of microprogramming. And the questions will come from basically beginning to that point, and this material will be in the final. Okay, so I would just say goodbye, and then we'll talk to you again sometime around Wednesday. Thank you.